It's opposite day, and we're going to talk about opposite particles. More specifically, we're going to talk about antimatter, because the particle colliders are at it again. Physicists at CERN recently announced the largest antiparticle ever to be produced in the Large Hadron Collider, antihyperhelium-4. Now, I'm not a particle physicist, so that entire name sounded like science fiction to me, which in turn got me asking, what the heck is hyperhelium-4, and how come the Large Hadron Collider created its antiparticle? First, a quick recap as to why we put so much effort into banging particles into other particles in the first place. Particle collisions let us make more particles, including antiparticles. More specifically, when it's doing that, it lets us do pair production. When we slam atomic nuclei into each other with tremendous energy, some of that energy can be converted to mass due to mass-energy equivalence. Thank you, Einstein. When that energy is converted to mass, sometimes the mass will have a charge, like how electrons have a negative charge. So since we have to conserve charge in the system, physics loves conserving things, it's so thoughtful. If we're creating a charged particle, we'll also have to create a particle with equal and opposite charge, which is the antiparticle. In the case of electrons, the equal and opposite is called a positron. Yeah, even though positrons seem normal because they don't have anti in the name and because we use them in hospitals for positron emission tomography, no, they're still examples of antimatter. But the whole point here is that by accelerating particles and smashing them into each other at very high speeds, we're providing a ton of energy that can be converted to mass, and it takes a ton of energy to accelerate particles enough to produce even a small subatomic particle, like a pi meson. It's made up of just like one little quark and one little antiquark, and it's still at least 264 times more massive than an electron. Now, when I talk about a lot of energy, I mean we have to use the particle's mass worth of energy, and then also the energy from conserving momentum of the original particles we smashed together. The unit we use for that is electron volts. And if you're smashing a proton into a static proton at high speed, it takes 290 mega electron volts of energy to make a pion with a mass of just 135 mega electron volts. The point is that you need to collide particles with a ton of energy to convert energy to mass. So as you create bigger particles, you're going to need more energy, a lot more. Say we want to create an antiproton. Well, first off, if we're smashing particles together to convert energy to mass, we're still going to conserve charge, so we won't just create an antiproton all on its own, no. We'll be creating one proton, one antiproton. But it'll take a lot of energy because protons and antiprotons are big. If our little pion made up of one little quark and one little antiquark, if that thing was 264 times more massive than an electron, yeah, a proton with 3, even just relatively lightweight quarks, still 1,836 times more massive than an electron, give or take. Our math said it took 290 mega electron volts to make that little 135 mega electron volt pion. Yeah, if we're making a proton and an antiproton, we need 6 giga electron volts. Now, we don't need the whole tera electron volt full power of the Large Hadron Collider just to make antiprotons. We were making proton-antiproton pairs back in the 1950s with our 1950s particle accelerators. But CERN didn't just issue a press release that they made antiprotons. They said they made antihyperhelium-4. I still haven't explained what that is. But I wanted to establish a sense of scale on everything that goes into even one proton-antiproton pair. So helium-4 has 4 baryons. It's got 2 protons, because that's what makes it helium. And it's got 2 neutrons, hence the 4. We talked about helium-4 when we talked about making new elements in a cyclotron, which, by the way, also a kind of particle accelerator, actually. Helium-4 is fun because it's also known as an alpha particle, so sometimes when a radioactive element like uranium-238 undergoes alpha decay, it'll just pop off a little helium-4 and turn into thorium-234. So anti-helium-4 is an anti-alpha particle, which is kind of cool. But more relevantly, it is a huge atom of antimatter compared to an antiproton, let alone to a little positron. Remember a few minutes ago we were like, yay, positrons are antimatter? And now we're looking at antiparticles that are like, I don't know, like 7,000 times the mass of that little positron? Good times. But anti-helium-4 wasn't first detected at CERN at all. It was found at a totally different particle accelerator, the relativistic heavy ion collider at Brookhaven National Laboratory back in 2011 as part of the STAR collaboration. That is the second highest energy collider in the world and creates collision energies up to 100 gigaelectron volts in the kind of experiment used to create anti-helium-4. Remember, it took 6 gigaelectron volts to make our little proton-antiproton pair? So the trick wasn't just to get enough high energy to create huge, massive antiparticles. I mean, that accelerator had the juice. But they also had to detect a very heavy antimatter particle that just wasn't going to be made in large quantities. With each increase in baryon number, remember it's 4 in the case of helium-4 or anti-helium-4, there's a 1,000-fold decrease in particle yield. The trick in that 2011 experiment was detecting a very heavy, very rare particle, and they correctly predicted that it was going to be the largest antimatter particle found for a long, long time. Which finally brings us back to antihyperhelium-4. What makes it different than the anti-helium-4 that we found way back in 2011? Well, the gimmicky answer is the hyper part. I'm so sorry, but that is kind of the correct answer. So helium-4 has 4 baryons. It's got the 2 protons and the 2 neutrons, and that's its cute little atomic nucleus. Anti-helium-4 has 4 baryons. Again, it's just the opposite charge. 2 antiprotons, 2 antineutrons. Yes, the neutrons are also technically anti, but it's just because it's made up of antiquarks. We don't need to worry about it. Antihyperhelium also has 4 baryons. It's just not the same 4 baryons. It has 2 antiprotons because that is what makes it antihelium. And it has an antineutron. But instead of that 4th antineutron, I can only describe the 4th baryon as exhaustingly quantum. See, the 4th baryon in antihyperhelium-4 is an anti-lambda particle, specifically an antihyperon. Hyperon? You might very reasonably ask. Is that a proton? No. Is it a neutron? Also no. But this thing has got 3 quarks, like a proton or a neutron? Yes. It's the what kind of quarks that matter here. Okay, not the best diagram, but here's a comparison of the 3 particles. Protons are made of 2 up and 1 down flavored quark. Neutrons, 2 down quarks and 1 up quark. The more I talk about up quarks, I feel like I'm on the cusp of an up dog joke. The kind of lambda particle we're talking about today has 1 up quark, 1 down quark, and 1 strange quark. Just like neutrons are a little more massive than protons, because down quarks are bigger than up quarks, and neutrons have 2 down and 1 up, lambda particles are heavier than either protons or neutrons, because strange quarks are heavier elementary particles than either up or down quarks. The strange quark's also what makes that kind of lambda particle a hyperon. Hyperons are apparently just baryons that contain only up, down, or strange quarks. So because that lambda particle has 1 of each, it automatically qualifies as a hyperon. Congratulations. In the antimatter version of these particles, all the quarks are flipped. So an antiproton has 2 anti-up quarks and 1 anti-down quark. The lambda baryon has 1 anti-up, 1 anti-down, 1 anti-strained, and so on. Like I said, it's exhaustingly quantum. The point is, antihyperhelium-4 isn't quite the antiparticle of a normal alpha particle, like the thing that we get from radioactive decay, like the product of that 2011 experiment. What we're dealing with today has got one of its antineutrons swapped for this weird, strange anti-lambda thing. CERN calls this the heaviest antimatter hypernucleus yet at the Large Hadron Collider, but it's also just a little bit short of the current heaviest antimatter record I could find. That, as far as I can tell, should go to STAR's observation of antihyperhydrogen-4 earlier this year, which has 1 antiproton, 2 antineutrons, and 1 anti-lambda baryon. Neutrons being a little heavier than protons, all things being equal, it gives the advantage to antihyperhydrogen-4 when it comes to total antimatter mass, just by that fraction of a quark. How come it took so long to get this incredibly weird, incredibly sci-fi sounding antihyperhelium-4? I mean, the Large Hadron Colliders had all this power the whole time. Well, in fairness, we actually smashed the particles into one another back in 2018. This new finding is the product of data analysis of those measurements back then. But really, why are we bothering with antihyperhelium-4 at all? What does it teach us that we couldn't learn from antihelium-4 13 years ago? The hope is that the behavior of hypernuclei, these atoms with a strange baryon in them, might help us solve the baryon asymmetry problem, also known as the matter-antimatter asymmetry problem. Ultimately, the biggest reason we're even doing particle accelerator stuff at all is to figure out why, at the beginning of the universe, we ended up sitting here being made of matter rather than antimatter, or rather than nothing at all. Quantum mechanics and the standard model of particle physics have yet to account for this problem. So when we create these weird particles like antihypernuclei with their little anti-strange baryons, we might see something in their interactions that accounts for why, in the high energy conditions at the beginning of our universe, there ended up being enough matter that didn't immediately annihilate with the antimatter so that we could actually, exist. And those answers may lie in the interaction of larger particles and antiparticles, not just the very smallest ones, which is why we keep making bigger, weird particles in these particle accelerators to try to find the answers. Yes, at some level, we explore exotic matter like antihyperhelium-4 because it's cool. Some science and engineering projects are justified in terms of what they can do for us as a society, but not everything, not always. Like, dinosaurs are cool. And it'd still be cool even if nothing we ever learned about dinosaurs ever helped us in any way. Like, making antimatter by smashing subatomic particles into one another is just freaking cool. And the fact that it can help us refine our theory of particle physics and tell us about the earliest moments of our universe just makes it even better. For my part, I think anything called antihyperhelium-4 is like dinosaurs. It's just cool. Happy opposite day, everyone. Should I say anti-happy opposite day? Yeah, I knew this story was strange.